All right, the next section we have is 6.4, which is the method of cylindrical shells, or more commonly referred to as the shell method. This is a different method for obtaining, or for a way to write down at least, the integral that represents the volume of the solid that's obtained from rotating a region about some axis in the plane. So far, we have learned and gone over both the disk and washer method. I say method, not methods, because really the disk and washer method is the same. A washer is just two disks subtracted from one another. Big disk minus little disk. When you subtract that smaller disk, you're essentially subtracting the volume, which bores a hole conceptually. It bores a hole through the volume. It hollows it out, a portion of it, creating a washer. So really, disk and washer method to me are the same thing. Shell method is substantially and conceptually it is different. Together, you will need to be prepared to work with and understand both of those methods, disk/washer method and the shell method. Together, these two things will hopefully allow you to tackle any problem you encounter. So in a previous video, example 5 of 6.3, I do this problem, given the region enclosed by y equals 2x minus x squared, x 0, and y equals 1. We went through all three, rotating about the x-axis, the axis y equals 1, and the y-axis. But when we did the y-axis, this last part, it was a little tricky because we had to find the inverse function. We had to somehow solve this for x, which involved completing the square, which is something it's a very common procedure in math. So it's something we're expecting you to know how to do, but it's also more work than what you should have to do for this problem, because this problem is much more readily accomplished by using the shell method. Okay, so what is the shell method? So the shell method is how we can build a volume. So the way I would think about it here is starting with this image. If we imagine drawing some line downward, and then imagine this line, just this line segment being rotated about the axis. Well, it would create this mirror image on the other side, and it would create this cylinder. It would create the cylinder. Now imagine that I did this again really close by. So maybe I did another one like right here. And then that's going to create, I'm doing it with a thicker, stroke width to emphasize that it's a second one. And then we again rotate this. And then if we did it again, we would create another little piece. And then if we continued this, just moving a little bit out more and then rotating again, moving a little bit out more, rotating again, and if we did this, we would basically think about a roll of toilet paper or a roll of paper towels or a roll of anything, gift wrap paper, anything. If you, let's say toilet paper, if we take toilet paper and we start with it with just the roll and no toilet paper on it, if we were to then put toilet paper on it, we would roll it around, forming these cylindrical shells. Because it's not a solid cylinder unless we started from the center. In this case, we didn't. But it's this idea of wrapping around these little shell around the outside. Or an even maybe a more extreme example is start with a tube and then paint it, let it dry, then paint it again, let it dry, paint it again, let it dry. And if you keep doing this, sure, the paint basically, when you apply one application of paint, you don't notice any perceptible or measurable increase in the diameter of that roll that you've painted. But you absolutely have added a little thickness. So we can think of that as like a dx or a change in radius dr, some little increase. And if you keep doing that long enough, you will make it as wide as you want it to be. So that's the basic idea of cylindrical shells, is that we are forming this little layer that we are going to wrap around, which will contribute to the volume. Okay, so let's erase this for a moment. And let's go ahead and basically say here, this is not a rectangle because this is a sloped. It's not actually, a rectangle. But what we can do here is approximate this with a rectangle. So imagine that, oops, let's make that a little bit less thick. So let's say here's xi. Let's say this is the rectangle that we're going to actually add. So then this rectangle would get rotated around. So we'd have the exact same rectangle, and it would be some distance away. So I'm just using this as my little measuring thing. Oops. So right there. So we have that, and then this would create this nice little cylindrical shell. Okay. So effectively, we need to figure out how much area are we contributing. And that's exactly why I like that analogy of taking a roll and then just painting it with some different color. Because it's that paint, it's that surface area that eventually, if you keep doing it, will contribute to the volume. We can think about increasing an object's volume is the continuous process of adding or thickening the surface area. So we can think of volume as thickening the surface area of an object. So if we were to take this and we were to paint the outside, we need to know what is that surface area. That's the analogy I'm looking for. So if you forget about the whole cylinder, let's just think the outside of the cylinder. The outside of the cylinder is just this line. So if that line gets rotated about, imagine that we take a pair of scissors and we cut this and then we unravel. So I'll say cut and unravel. What do we have? Well, if we do that, we should have something like that. Rectangle. So this distance here is the height, let's just call it. And then this length here would be the circumference. Okay. So the circumference, remember, is always found by 2 pi times the radius. So the area of this contribution is going to be 2 pi times the radius times the height. And that is exactly what we have right down here. We can approximate the volume by saying the volume changes by adding up all these little additional areas with a certain associated thickness. A certain thickness. So in this case here, this thickness would be what we get if we just call this distance here dx, or in the sum delta x. It's this thickness here. Okay.